look after the pennies and the pounds will look after themselves. It's a cliche that parents share with their children to teach them the value of money, to plan their expenditures, to not overextend themselves. And it's wisdom that holds, even in high-energy particle physics. Some argue that the field of particle physics is in crisis. Influential voices argue that a larger, higher energy, more expensive discovery collider is currently not worth the financial outlay. While I disagree with their point of view, there is no denying that new discovery machines, like the proposed circular collider at CERN in Geneva, will come with monumental price tags in the tens of billions of dollars. Cautious voices note that while the size, energy and cost of discovery machines continues to increase, the physics case for their creation may arguably be becoming less compelling than it has been in the past. Until now, we have always had a credible, widely accepted prediction of the energy scale at which new, previously undiscovered particles or fields would present themselves. In the late 1970s, physicists predicted that the weak bosons, the W and Z, likely had masses of roughly 100 giga-electronvolts, and proposed colliding protons and antiprotons in existing synchrotrons to find them. Both particles were promptly directly observed by such experiments in 1983. In the 1980s, physicists predicted that the Higgs boson should have a mass of less than 500 giga-electronvolts, and proposed building the superconducting super collider in Texas to smash protons together at energies even higher than those at the current Large Hadron Collider, and to find it. Despite the failure of the SSC project, the later Large Hadron Collider dutifully found the particle in 2012 during its first run. By contrast, in the present day, we currently have no widely accepted hypothesis regarding the energy scale at which new physics may appear beyond the electroweak and Higgs scales. Some fear that a particle desert exists just beyond our current energy reach, a desert that we may not be able to traverse to reach the oasis of new physics, but could spend incredible amounts of effort, time and money wandering. Under this current paradigm, physicists such as Professor Peter McIntyre argue that successfully selling a new, higher energy discovery collider to funding agencies and the public at large will mean proposing machines that facilitate the absolute largest leap forward in collision energy for a given financial outlay. If we're going to leap forward into the unknown, let's leap as far and as cost effectively as we possibly can. He argues that a discovery collider could and should be situated in the ocean. Today, we will discuss his vision for a collider in the sea. Perhaps the water of the ocean is the natural counter to the particle desert. So how could a collider in the sea help us to search the terra incognita of the high energy regime with maximum cost effectiveness? Well, before we can understand that, we need to understand the major cost drivers of a discovery particle collider. A collider capable of producing particle collisions with an order of magnitude higher energy or more than the Large Hadron Collider. Collisions of 100 tera electron volts or more. In the current paradigm, the cost of such a machine is dominated by the cost of the double ring of superconducting magnets required to keep the protons circulating on circular paths, and the costs of boring tunnels to site the machine deep underground to avoid obstructions and provide radiation shielding. Stronger superconducting magnets mean that protons can be turned in smaller circles, and colliders can be more compact. However, contemporary superconducting magnets show a broad cost per energy reach minimum in the 3 to 4 Tesla field strength range, with costs increasing rapidly as the field strength increases to the 10 Tesla magnets used at the Large Hadron Collider, and even more steeply as the field strength increases to the 16 Tesla magnets slated for the future circular collider. Superconducting magnets no one currently knows how to build. If we want to optimize the cost effectiveness of the magnets as we reach out into the energy frontier, economics dictate that we should deploy superconducting magnets with a field strength of roughly 3 to 4 Tesla. We need to make our magnets weaker than those at the Large Hadron Collider, meaning that they cannot turn protons in such sharp circles, and the radius of our machines becomes larger. However, as the radius of an accelerator expands, so too detunneling costs. The cheapest and fastest tunnel boring ever achieved by a particle physics project was during the boring of the superconducting Super Collider tunnel through Austin Chalk near Waxahachie in Texas. The rock is soft and easy to bore, with every meter tunneled costing around $3,000. By contrast, the boring of CERN's Large Electron Positron Collider tunnel through less favourable rock in the Rhone Valley costs 3 times as much per meter tunneled. And the boring of a 90-kilometre long tunnel for a discovery machine like the proposed Circular Collider at CERN would likely cost even more per meter, as the tunnel will need to traverse many different types of rock strata. The realisation is that we're fighting somewhat of a losing battle when pushing for colliders with energies tens of times or more those of the Large Hadron Collider. To make our magnets as cost effective as possible, we want to utilise weaker magnets. But using weaker magnets means machines have to be larger. This larger size tends to decrease the cost efficiency of tunnelling efforts, and also means that we struggle to site ever larger machines at strategic geographical locations. Projects like the Future Circular Collider intend to use stronger, less cost-effective magnets to ensure that the machine can fit within the geographical constraints of the Rhone Valley around CERN. At current market prices, the superconducting wire required by the proposed 90-kilometre long 100 TeV Future Circular Collider at CERN could cost as much as $20 billion, while the boring of the tunnel could cost an additional $4 billion, giving the FCC a final price tag of more than $20 billion. By contrast, if we were to site a 100 TeV Proton-Proton Collider in Texas, use 3 to 4 Tesla field strength magnets, and bore a much longer 270 kilometre long tunnel through the soft Austin Chalk, the project could cost a fraction of the price. The conventional wisdom of locating high field magnets in underground tunnels is not the most cost-effective path to colliders even a single order of magnitude higher in energy than the Large Hadron Collider. So if financial outlay is our main concern, we need to be looking for large circumference sites with easily tunneled rock and building massive colliders that require moderate strength magnets. That's how we leap into the energy frontier with maximum cost effectiveness. If we cling to the current paradigm, claims of wasted funding will always have at least some purchase. Of course, even if we choose to site discovery machines in huge tunnels bored through soft rock and deploy the most cost-effective magnets, tunneling costs are still going to be significant. This is where Professor McIntyre and his team's intriguing proposal comes in. What if there were a location on the Earth where we could site a massive collider, utilising highly cost-effective steering magnets with moderate field strengths, without the requirement to bore massive, expensive, cost-inefficient, and geographically constrained tunnels? What if we could build a massive collider ring and get rid of the tunnel entirely? What if we could build a collider in the sea? McIntyre's proposal is to build massive collider rings skirting the continental slope in the Gulf of Mexico. These collider rings would sit neutrally buoyant in the sea at a depth of roughly 100 meters. McIntyre notes that a 270 kilometer long 100 TeV Proton-Proton Collider in the Gulf of Mexico could achieve similar collision energies to the proposed 90 kilometer long Future Circular Collider at CERN, but would use far more cost-effective magnets and negate the need for tunnel boring. However, McIntyre doesn't stop there. He believes that the Gulf of Mexico could become the site of the ultimate Hadron Collider, a 1,900 kilometer long machine capable of reaching collision energies of 500 tera-electron volts, 50 times the collision energies at the Large Hadron Collider, and 5 times those at the planned Future Circular Collider. If we're going to dive cost-effectively into the high-energy regime, we might as well dive as deep as geography and our ingenuity allow. This gargantuan ring would be built from 6,300 meter long half cells, consisting of a double ring of superconducting magnets inside a cryostat cooled by liquid nitrogen and liquid helium. The clockwise and counterclockwise beams circulating around the ring would be brought into collision in detectors enclosed in massive bathyspheres, also suspended at neutral buoyancy beneath the ocean surface. These bathyspheres would be the size of the underground CMS cavern at CERN, 30 meters in diameter. Such a machine would not only allow us to dive deeply into the murky waters of the high-energy frontier, but would have a myriad of other benefits. The machine would have a lower power consumption than a machine using stronger magnets to achieve similar energy proton collisions using a more compact ring. When charged particles like protons are accelerated in circular paths, they radiate away power in the form of synchrotron radiation. The smaller the radius of the accelerator, the tighter the turns the protons have to make, and the more power that is radiated away. That's why high-energy particle colliders have to be so large, to limit those losses. However, building an incredibly large 1,900 kilometer long collider ring limits synchrotron power losses relative to a machine attempting to create similarly powerful particle collisions using a more compact accelerator ring. That means that a collider in the sea would be an extremely power efficient and environmentally conscious way to reach 500 tera-electron-volt collisions. More on that later. A 1,900 kilometer long collider in the sea would also be able to deliver a massive amount of proton collisions for study due to the dynamics of proton beams at incredibly high energy. As beams of protons circulate in a particle accelerator, they emit synchrotron radiation, which reduces their energy and their momentum in all three dimensions. However, the protons are constantly being accelerated along the line of the accelerator ring, and their forward momentum is being boosted and restored. This leads to a phenomenon known as radiation damping. As the beams circulate, they actually shrink in the directions perpendicular to the direction of motion and become brighter and more focused. On the flip side, the beams are constantly broadening due to proton-proton repulsion within the beams and other non-linear dynamics. At a collider like the Large Hadron Collider, radiation damping is so weak that it has very little effect on the brightness of the beam. But at a collider in the sea, the energy of the beams will be so massive that radiation damping would win the tug of war and actually brighten and focus the beams of protons as they continue to circulate. During the operation of a proton-proton collider like the Large Hadron Collider, protons in the circulating beams are used up in proton-proton collisions, and the proton beams become depleted. The rate of proton collisions massively reduces, and below a certain threshold, the beams are dumped. The machine is then refilled with fresh, highly populated proton bunches, and the machine is restarted at an acceptable rate of proton interactions. This is a batch process and involves a lot of downtime where the accelerator is not producing proton-proton collisions for study. However, something amazing happens at beam energies as high as those envisioned by a machine like the collider in the sea. During 6 hours of operation, half of the protons are lost from the beam. However, unlike at the Large Hadron Collider, the proton collision rate doesn't plummet, because during that same time period, the beams have reduced in radius by a factor of 5 to 6. The interaction rate of the remaining protons roughly doubles, and the overall proton-proton interaction rate can be maintained at a roughly constant and phenomenally high level for long periods, facilitating a massive amount of data taking. Periodically, a fresh fill of proton bunches would be injected into a secondary ring and accelerated to an intermediate energy. The collider bunches would be decelerated to that intermediate energy, and the bunches would be stacked next to one another. The stack would then be re-accelerated to full collision energy, and data taking resumed. This constant luminosity operation is known as bottoms-up stacking, and is the optimum way to operate a 500 tera-electron-volt collider. It minimizes data taking downtime and makes analysis of proton-proton collisions easier, since many of the backgrounds and detector responses that plague downstream analyses are luminosity dependent. So it's clear that a collider in the sea would be a phenomenally powerful tool to help us set sail across the choppy waters of the high energy regime. But how on earth would we build such an incredible machine? Well, McIntyre and his team suggest that the half cells that make up the collider, consisting of magnets housed in sealed cryotubes, could be fabricated at a nearby port on the Gulf of Mexico. These half cells would then be taken out to sea on a modified container ship lined with deck cranes and lowered into the water. The half cells would then be sunk to depth by pumping water into or out of the half cells and connected to one another at depth using connecting valves protruding from each end of the half cells. The entire construction would be performed by modern submarine remotely operated vehicles, or ROVs. No human would ever enter the water. It should be noted that a single particle collider cannot accelerate protons all the way from rest to a massive energy like 500 tera electron volts. There would need to be a series of lower energy feeder rings like those at the Large Hadron Collider. The main collider ring of a collider in the sea would likely require a roughly 12 tera electron volt booster ring for injection, an accelerator as powerful as the current Large Hadron Collider. This ring would inject protons into the main ring for final acceleration to maximum energy, and would also be used for bottoms-up stacking. That ring would in turn require an approximately 600 giga-electron volt booster, and that booster would require a roughly 10 giga-electron volt pre-booster. This lowest energy 10 giga-electron volt pre-booster could be the first actual accelerator in the sea, where physicists could develop and prove in practice many of the hard technical methods for operating an accelerator underwater. This all sounds incredibly promising and exciting, but the rock caverns of historic particle colliders are far less fluid and mobile than the depths of the ocean. Operating particle accelerators in a constantly churning medium will be a phenomenally difficult task. For one, how can we ever hope to keep such a beamline well enough aligned to facilitate massive numbers of proton-proton collisions? The depths of the sea in the Gulf of Mexico are subject to ocean currents, infrasound pressure waves, and local changes in buoyancy depth caused by warming and cooling of the ocean water. The dominant current in the Gulf is the loop current, which flows between Cuba and Yucatan, loops close to Florida's west coast, and then passes into the Atlantic. The western part of the Gulf has no prevailing current and contains slowly evolving eddies that cut off from the loop current, drift westwards, and dissipate. The currents at 100 meter depth tend to be gentle, with an average speed of 12 centimeters per second, but can reach a maximum of 1 meter per second. These currents are incredibly variable and would create continuously changing pressure fluctuations on a beam pipe at depth. Studies at depth in the Gulf of Mexico show that these pressure fluctuations would have two frequency components: slow fluctuations with a frequency of less than 0.02 Hz, and faster fluctuations with a frequency of 0.1 to 1 Hz. These fluctuations are caused by phenomena such as seismic waves, long-range currents, temperature variations, and more. The position, alignment, and buoyancy of half-cell segments of a collider in the sea must be maintained to minute accuracy, despite these constant fluctuations. Otherwise, circulating protons will simply collide with the walls of the beam pipe and be lost. How can this be done? McIntyre's team proposed that a laser could be fired in both directions along the axis of each beam pipe half cell. The spot this laser hits can be measured at the connection points between half cells. If a half cell twists or moves out of alignment, this will show up in the detection point of the laser at the connection points. Computer algorithms can then determine the misalignment of the half cell and work to bring it back into alignment in real time. Low frequency changes in alignment can be corrected by connecting powerful 50 megawatt marine thrusters to each half cell that facilitate both horizontal and vertical thrust. Marine thrusters are used routinely in marine power to precisely control the direction and thrust of a vessel, or to station keep a vessel with precision. Computer control can speed up and slow down these thrusters and change their alignment to restore the relative alignment of half cells to 1 centimeter precision, and maintain the beam pipe's overall position in a prevailing current, even when a hurricane passes overhead. However, such thrusters would likely not be responsive enough to correct the higher frequency changes in alignment of the beam pipe. As such, a trim dipole, an additional magnet in each half cell, would be rapidly powered up or down to deflect the circulating protons by minute amounts and allow them to follow the path of a beam pipe that is deforming by small amounts in real time. An absolutely amazing possibility. Maintaining a stable, viable beam pipe 100 meters under the sea and against prevailing currents and pressure fluctuations is one of the massive challenges that stand in the way of realizing this intriguing machine. However, there are potential additional benefits to developing the station-keeping technology we've just discussed. It could also be the key to powering a truly green collider. There is a massively growing interest in offshore wind power, but sources are limited to the continental shelf of a nation. The arc of the collider in the sea and its boosters would offer a potentially game-changing opportunity to integrate a string of wind turbines on the surface just above the arcs of the rings that are over the continental shelf, but utilize the same station-keeping technology to maintain the positions of each turbine. These turbines could make power connections to the submerged particle collider using a superconducting transmission line that could run at the same 100-meter depth as the collider. What's being suggested is that the collider in the sea could conceivably be powered by a huge offshore wind farm following the path of the collider in the Gulf of Mexico, with 5 megawatt wind turbines spaced at roughly 150 meters along a 1,000 kilometer arc, providing 35 gigawatts of power and minimizing the collider's carbon footprint. The amount of electrical power that could be generated would be able to power the entire south-central US and eastern Mexico when the collider is not in use. Not a bad payoff for high-energy physics. Connections from the collider to the mainland would be made through massive umbilicals at locations where it passes closest to the land: Houston, New Orleans, and Yucatan. These umbilicals will carry superconducting transmission lines for power, cryogenic coolant lines, and instrumentation connections. So it seems that a collider in the sea might not be as far off into the realms of science fiction as we might initially expect. However, what are the potential showstoppers that could sink a collider in the sea? Naturally, there is a radiation concern. Particle colliders produce a large amount of hard radiation in various forms. Could this radiation pose a danger to local human populations or local wildlife? Well, the site of the collider in the sea has been chosen to be beyond the regions that are used most often for shipping, oil wells, fishing, and recreation. In addition, water is an excellent radiation shield and nature's radiation absorber, meaning that radiation is unlikely to travel far from the path of the collider or any interaction points. The dose at the surface would be minuscule. The activation of materials and creation of tritium by radiation exposure are also many orders of magnitude below the levels that are already produced continuously in the sea by cosmic rays continuously bombarding our upper atmosphere. The impact on human and wildlife should be minimal. However, one does wonder if we might be able to see a ghostly Cherenkov glow close to the path of the collider. Underwater maintenance of the collider would also be extremely difficult. However, Professor McIntyre contends that ROVs are used routinely in marine technology applications, for example the exploitation of offshore oil and gas, and that the requirements for installation and maintenance of a collider in the sea are not beyond the capabilities of technology already in routine use. Obviously, a lot of work needs to go into perfecting the installation and maintenance methodologies, but such is the case for any new discovery collider. So given the cost effectiveness and technical feasibility of a collider in the sea, you might be left to ask, why has it received so little fanfare in the particle physics community? Professor McIntyre himself notes that when presenting the concept of the collider in the sea to collider experts, he has frequently been told that this is just not how we build colliders. Perhaps the real showstopper for a collider in the sea is just that it is so radical. Building a larger electron-positron collider at CERN, followed by a larger hadron collider, the future circular collider plan, is a game that we've played before with LEP and the Large Hadron Collider. It's something that's worked before. It's something we understand. By contrast, a collider in the sea comes with a myriad of new known and no doubt unknown technological and logistical challenges. The high-energy particle physics community, especially in the United States, was shaken by the cancellation of the superconducting supercollider in 1993, after more than 20 kilometers of tunnel had been excavated and more than $2 billion had been spent. Another venture to build new labs and huge amounts of infrastructure far away from established hubs such as Fermilab or CERN may still feel like a step too far. On the flip side, perhaps in some senses, the collider in the sea isn't radical enough. The Collider in the Sea plans to utilise currently available magnet technology that can be rapidly and cheaply produced by industry to keep costs down. However, alternate proposals for high-energy discovery machines, such as the Future Circular Collider or the Muon Collider, will require immense technological research and development to be realised, and hence promise huge advancements in fields such as magnetics, power distribution, cooling systems, and more. Is the field prepared to forsake such symbiotic technological advancement opportunities? Perhaps that's why many might not have heard of the concept of a collider in the sea, because it falls between two stalls. Despite the current impression that machines such as the Future Circular Collider at CERN and the Muon Collider, potentially sited at Fermilab, are being floated as the likely successors to the Large Hadron Collider, Professor McIntyre and his team intend to continue their work on the Collider in the Sea concept and even produce a half-cell prototype. They intend to run more simulations of the long-term bottoms-up stacking beam dynamics of a collider in the sea and determine whether dynamic beam pipe corrections and terrain following are feasible. Eventually, they plan to sink a prototype half-cell complete with a superconducting dipole, cryogenic systems and power systems into the depths of the ocean off Texas and power it up. If they can achieve these milestones, this science fiction could one day become an affordable reality. The Collider in the Sea is a radical proposal. It fundamentally challenges the conventional wisdom that building particle accelerators requires rock tunnels, stability, and solidity. It also challenges the particle physics community to forsake the life preservers of CERN and Fermilab and venture back into treacherous waters that have turned on them before. However, such a machine could allow us to set sail efficiently and far across the uncharted oceans of the high-energy regime. Perhaps during a time when many doubt the wisdom of continuing to push forward, we instead need to push downwards and consider a new, more cost-effective route to high-energy collisions. More than 70% of our planet's surface is covered by oceans. When we're struggling to find space for the cost-effective development of projects that will illuminate the depths just beyond our comprehension, perhaps the very depths of our planet could be our salvation. What we know about our universe is a drop in the ocean. Perhaps with a collider in the sea, we can squeeze out a few drops more. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.